Okay, so what we're gonna do is look a little bit, I think, at chapter 5, then go back to 4, and then we're probably not gonna have enough time to go back to chapter 5 for the end of today, but we'll see what happens. So where we ended yesterday was looking at some of the common names for some of the groups within our periodic table. We added a couple of extra little terms for this, or extra terms within this. Group 3 to 12, commonly known as the, anybody? We're looking at the transition. That doesn't look spelled right. I don't think that is right. Transiton? Close enough. Looking at our transition metals, then we've got elements 57 to 71 and 89 to 103. 57 to 71 are known as the lanthanides, and the other one are actinides. Collectively, they are known as the inner transition elements.
Are you going to explain what all of those are, what it means? Like, what does it mean? Like
That's spelled right.
nitrogen?
So, as far as what they mean,
Yeah,
what is this object?
that's a table.
Okay, what does that mean? So what it is a word that represents all of those elements. So the word nitrogen is in reference to all of the elements under nitrogen. Okay, so that's all it really means. Where that word came from, the root of that word, I'm not going to tell you because I don't know. Okay. The next, I would say, more important question is, of those, which ones should you absolutely know? Which ones would you be tested on? So I would absolutely expect you to know your halogens, the noble gases. I'm actually also going to expect you to know what the transition metals are. And just because I think it's, even though I can't spell it, knowing your inner transition metals as well, being able to reference those. The alkali and the alkaline earth metals, in all honesty, probably any professor in this class would have you memorize that, but I've always gotten them backwards and can't seem to remember them, which one's which. So if I can't remember it and it's something that I find kind of pointless to memorize, I won't make you responsible for it. Okay. So what's circled in blue are the ones that I would fully expect you to know. The alkali and the alkaline earth, moving into a different class, almost guaranteed you're going to be expected to know those as well. I know those terms. The nitrogens and chalcogens, you will probably never be expected to know. You might see those two phrases come out, or those two words show up in your textbook or other textbooks for future classes, but I doubt any professor would ever test you on that, on knowing the names for those groups. Okay? Other questions about those? I did answer your question.
Like on the test, will you ask us like which one is transition metal, or is this a transition metal?
Yeah.
Or is
So
this part
I
of the
could give
noble
you the
gases?
symbol OS and say to which group does it belong, and then your multiple choice would be halogens, noble gases, transition metals, inner transition metals, and goats, or none of the above. Okay, I'm not very creative apparently. So what would you do? You need to figure out where OS is on the periodic table. I just saw it. 76, which shows up in which section? That's group 8, which is in our transition metals. So your answer would be transition metals. Okay. Does that make sense as far as what kind of questions you could get with that? Is that another hand?
Ton of questions like that?
Ton of questions like that? No. 2 or 3 at most.
What about like LA or LU?
Which one do you want, LA or LU?
One of them that's both, it's in between the 57 and 71 on the elements, but it's also a transition metal that's in the third group.
So 57 through 71 are not technically transition elements. They are inner transition metals.
So that fits whatever group they're in.
Yeah. Because it's breaking as a subcategory from that section. Okay. For the same reason that boron is not a transition metal. Okay. Or gallium being a transition metal. Okay.
What's that last word, the lanthanide?
Actinides or lanthanides? Lanthanides, which could easily be misspelled in that case. But it's coming from the element lanthanium. And then actinium. All right. Now what we're actually going to start to do is look at a real quick, simple periodic trend, try and come up with some explanations for why this trend is true. We're going to find out why it's wrong, and then we're going to double back to chapter 14 to kind of come up with an explanation for why the trend actually makes sense. So one of the big trends that we can pick up off the periodic table is something about size, or the atomic radius. All right, so we get two primary trends for an atom that we can find on our periodic table. So what we want to do first is kind of address, I got more information at the bottom of the slide than at the top, address what's happening as we move through our periodic table. So as we go from hydrogen to helium to lithium to beryllium, to boron to carbon, what's happening to the atom? Not even atomic radius.
It's heavier.
I don't even want to get into weight either. Weight gets towards the idea. Why is it getting heavier? What's increasing? Amount of protons. What else? Amount of neutrons. And the amount of electrons. So all of those are increasing as we go through our periodic table. Okay? Every single element we move up is increasing both in protons and in electrons, and typically in neutrons too, though I'm sure we can find an exception with that. Okay? So why is that important? Well, atomic radius is going to be how big is the shape that holds all of those individual things. So let's think back to those particles and say which of those are going to contribute most to the atomic shape, okay, or that atomic size. Where are the protons and the neutrons found? In the nucleus. So that's where they are in hydrogen. What happens when we move to helium? Where are your protons and neutrons? Still in the nucleus. How about when we're at silicon? Still in the nucleus. Okay, so our protons and neutrons are always in the nucleus. And as we add more protons and neutrons, we might expect our nucleus to get bigger. So that could contribute to our atomic size. Remember way back when we started first talking about atoms, and we said, okay, let's take the nucleus and make it the size of a marble. How big was the atom in comparison to that marble?
Stadium.
Superdome, okay, a stadium. So yes, increasing the numbers in protons and neutrons does appear to expand the size of the nucleus. Is that really what's defining the shape or the size of our atom? No. What's contributing to the size of our atom is the electrons. Okay? And as we move up, we're still adding electrons, so it makes sense. The more electrons, the bigger we get. So really when we're looking at our size, okay, or our atomic trends, we would predict that as we increase electrons, we would predict it to get bigger. Okay, so we get two main trends, and they go kind of in order of importance here. So the first one is looking at how the radius changes when you look within a column. So as we move from hydrogen to lithium to sodium to potassium to rubidium to cesium to francium, what happens to the atomic radius? Well, think back to what's happening with our subatomic particles. Our protons and neutrons go up, but that has no effect in reality towards our atomic size. But what happens with our electrons? The electrons go up a lot. So what would we expect to happen to the size as we move from hydrogen to francium?
Get a lot bigger.
We would expect it to get a lot bigger. So as we move down a column, we would expect our atomic radius to increase or get bigger. For some reason, I see that increase moving down the column easier than I see what the textbook slides are showing here, which says the atomic radius decreases as you go up the column, okay, up within an individual group. So make sure you're careful with the frame of reference on what you're looking at. When they're saying decrease, they're going up the column. When I say increase, I'm looking at it going down the column. So make sure that when you try and define your atomic radius definitions that you know which way you're looking at. Okay? So that one seems to make sense. Put more electrons in, gets bigger. What about when we move across a column? So let's ignore what the slide says for the moment. As we move from, say, lithium to beryllium to boron to carbon to nitrogen to oxygen, fluorine to neon, what's happening? Okay. We're putting in more protons and neutrons. Again, that's just the nucleus. We don't care about that. We're putting in more electrons. So what would we expect to happen to the size? Should get bigger. What happens? So we move to left to right on the periodic table. What happens to the atomic size? It decreases. It gets smaller. That's a really odd observation. We put in more things, and yet somehow it compacts tighter down. It's a very odd relationship. Okay? And one that we don't have the tools to really understand yet, because what we're talking about here is where the electrons are. Well, do we know where the electrons are around the individual nucleus? We defined anything about where they belong to, at what point? No, we just said they're somewhere around the nucleus. Okay? Well, it turns out that they have to be in very particular positions. Okay? Those particular positions, there's multiple pieces of evidence for. One piece of evidence is this atomic radius issue. Okay? As we're adding more electrons in, we would expect it to get bigger. If it's not getting bigger, those electrons have some weird special circumstance that's affecting that atomic radius. So they have to be existing in very particular spaces to allow that atomic radius to not increase. Does that kind of make sense?
So they're just like super compacted.
I wouldn't call them super compacted, but they're going into the same space. So relatively they are compacted, kind of. Okay. I just don't like that word necessarily. Okay? So when it comes to atomic radii, the one down the column, everybody should be able to pick that one up. The one across your rows, that one gets a little bit trickier. Okay? And until we actually talk about where the electrons actually exist and have some understanding of what electrons do or where they are, we can't really explain that observation yet. Okay? Next big thing would be kind of looking at some examples. So when we go down a column, the example I picked was the alkali metals, that first column. We notice the size increases. When we look in that first row, as we move from lithium over to fluorine, you notice that the size decreases, but we don't see as drastic a change as we see going down the column. Okay, which is kind of a neat observation that plays an important role when you move into organic chemistry. In a row, your size does decrease, but it doesn't decrease that much. Okay? Which is why it's rule number 2 when we're looking at atomic radii. Okay? Kind of makes sense? So far, at least. Questions about that? Okay. You'll notice that we don't look at the transition elements. Any ideas why? Or even the inner transition elements? Yeah, we start to see exceptions to these rules. Okay, so we've got to be a little bit careful with some of the trends that we pick up in the periodic table. Sometimes we'll see exceptions. For the most part, when we're looking at those first 2 columns and the last 6 columns, we hold pretty true to these general trends. Yeah?
So do we need to know which ones affect these ones, and which ones are the exceptions to the transition elements for the test? Is that going to be on there?
Nope. There's a very good reason the transition elements aren't shown here, because I don't want to get into that whole exception jump. Leave that for a more advanced class. Okay? What I expect you to know is the general trends and pick those up. All right? So one thing you could go through and do is take your periodic table. You'll notice this one actually has the transition elements in it, and they're trying to show probably atomic radius in that third axis, the one kind of going up. And you notice if you take a look at the transition elements, you do see some exceptions. It doesn't constantly go down. For instance, right in here, manganese and technium don't continually decrease in size. Okay, so your atomic radius trend doesn't hold very well through the transition element range, and there's a variety of explanations for those. Okay? So what you could do to help remember these is you could set up something along these lines as the arrows have in this. So when you take a look at your exam, you could probably draw a crude periodic table. Say, here's my periodic table. Okay, and you could remember maybe francium and helium. And you could add some arrows and put in your decrease and your arrows, metallic, decreases as well. Decrease, this was what, radius. In theory, you would write more neatly than that, but it gives you an idea. So when you get to your test, and if you ever were asked a question about it, you don't have to think about those trends. You go back to what you got drawn, and you've got your trends drawn on it. Okay? I, again, have problems with the whole decrease thing. Whatever you decide to do, if you want to measure increase or decrease, just make sure that you're correct when you come up with your arrow scheme. Okay? I've already talked about increase because that's the one that I see preferentially. So if I drew it out, I probably wouldn't be drawing decreases in each of these cases. I'd be going through and putting in increases, and my arrows might look a little bit different than this. So you have to decide what's most comfortable for you to make sure that you can pick up these trends. Okay? Questions about that? Yes?
Maybe fall off that a little bit, but
Nope.
the atomic radius, there's no way to find any of that on the periodic table. We just have to put a note.
The number for the atomic radius you do not need to know. What you would need to know is the trend.
Okay.
So if on the test I gave you, let's see if I can do this. Let's say you're given rubidium, sodium, lithium, potassium. Say put those in order of increasing atomic radius.
Okay.
So you would then need to know the trend within the periodic table to set up and get that answer correct. So you'd then organize that such that you got your increasing atomic radius. Does that work? Okay. You'll notice that we added an extra thing in red. What's the red in reference to? Metallic character. Notice our metallic character appears to follow our atomic radius pretty well. That's why they drew it on there like that. Okay. Does that make sense for our lower left-hand corner to be the most metallic? Okay, where do we transition from being metallic and non-metallic? Could you point to it on the periodic table? We can point to the ones on the wall because they're a little bit easier. Where's our, or actually we could even use the one that's up on the board.
Green.
Our green elements are what? Not our transition metals, but our metalloids or our semi-metals. Why are they semi-metals, or why would you even refer to them as transition metals? Well, that's a bad reference. Don't make that one. What's happening as we move through the semi-metals? We're moving from metal to non-metal. So if we look at our left to right transition, as we move through that, metal, metal, metal to non-metal. Which is more metallic, the left side or the right side of the periodic table? Left side. If we go up, metal, 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 that's a bad column. Metal, semi-metal, non-metal. Which is more metallic, top or bottom? Bottom. So our lower left-hand corner is our most metallic. Our upper right hand is our least metallic. So that can help us see that transition in those trends as we move through the periodic table. Okay? Questions about those trends? Okay. Predicting physical properties. This is what I should have had this slide back when we were talking about Mendeleev. I thought it was going to show up there. One of the things that you'll see in the homework as well as potentially on the test. Okay? And this is why Mendeleev was so cool, or why he was given so much credit, was because of this ability. So what the question's asking here is, what can we predict about francium? So first off, to answer that question, what do we need to know? What's that? We don't even need a trend. Where it's at on the periodic table requires another piece of information. What's the symbol for francium, which is FR. So we could go ahead and put that down here. Where is FR? Underneath CS, or cesium, which is underneath rubidium, underneath potassium, underneath. Okay. So what we're doing with these physical properties is that we noticed, when we organize these, that we noticed some trends. Okay. Can we predict the atomic radius for francium? So to do that, what's the first thing we could do? Okay. We've known our trends. Our trend says that francium needs to be bigger than CS. Good. How much bigger? What we can do to figure out how much bigger, we can go back to our other elements and look at the differences between these. What's the difference between the first two? Right? Roughly 0.03. How about the next two? Roughly 0.04. How am I figuring out these differences? Subtracting the two. What's the next set? Does that look like 2? Next set. Okay. So francium. Does it make sense to go through and call it 0.34? Why not? That jump going from cesium to francium is too big of a jump. Okay, we know it needs to be bigger, but how much bigger? Well, as we look at the trend as we move through, in general, it's only going up by 0.02, 0.04 at the most. And the last two only went up by 0.02. So as a reasonable guess, we could probably say the radius is 0.286. Okay. So what we're doing is guessing based on the information we've got. It's an educated guess. It's not just a blind guess. How about the density? What trend do you see with the densities? In general, it looks like the densities are increasing. So what might be a reasonable guess for francium as far as the density goes? A number bigger than 1.87. Okay, how much bigger? Well, to do that, we'd go back to our differences. What's the difference in here? Do we want to call that 4? Okay, I'll accept that. Difference there? Actually went down, right, by roughly 0.1. Next difference? Up by 0.7. Next set? In general, it's increasing. Okay. It is an in general process. We do have that negative one in there. Okay, so we might say it'll go up by 0.3, maybe 0.2. So we could take a stab at it and say it's roughly 2.10 for its density. Does it make sense as far as how we're predicting these numbers? Should I do another one, or are you guys happy with that? Huh? What do you mean?
It's not following a pattern.
It's not following as nice of a pattern. But if we look at the overall trend, 0.5 to 0.9 is going up. 0.9 to 0.8 is going down, but not by a huge amount, particularly in comparison to the up. We look at the next one. Going up. Next one. Going up. So the general trend for the density is that it's going up. Okay, you could look at the stock market. The general trend for our stock market is going up. Does that mean it never goes down? No. Oh, over the last 100 years, it's been going up. Okay? So we can look at a general trend and try and apply the general trend to it. It doesn't have to be exact. Remember, this is a guess, but we're trying to make it as educated of a guess as possible based on the patterns that we've seen so far.
Would this be not like a multiple choice on the exam, but more like handwritten and you just are looking at our work? Or?
So I could do it as, I probably wouldn't do it with the density because that one's a little too variable. But you could see it as a multiple choice for, let's see, is melting point consistent? Melting point looks consistent. Let's take a look at melting points. I'm going to clear everything. And let's see, I'm going to have to draw in some of the work here. What are our differences between these? First set is what? Roughly 80, right? Next set. Oops, that's almost 40. Next set. 40 minus 20. Next set, minus 10, right? So as we go down our column, we see the melting point decrease. Okay? And not only is it decreasing, the amount that it decreases also decreases. So, multiple choice question. Melting point possibilities. I could ask or give you as an answer, let's say, let's go with, how about this? -5 degrees Celsius, 18 degrees Celsius, 35 degrees Celsius, and why not? 180 degrees Celsius. Which of those?
18 degrees Celsius.
18 makes the most sense for our answer and for the trends that we see.
Okay.
All right? So it's going to go based off of those general trends on what we're trying to do and predict. Okay? As the morning pointed out, there's another piece of information that we could look at. All of our phase information, solids, liquids, and gases, is at room temperature. What temperature is room temperature? Roughly 22 degrees Celsius. Okay? Which means if our melting point is under room temperature, what phase would it be? Be a liquid. We take a look at francium, what phase are we specifying it as? Solid. What should our melting point be? Should probably be no lower than 22 degrees Celsius. So we could add in another layer of difficulty to that. Okay. I don't think I will do that. But what we're trying to do is evaluate based on all the information that we have at hand. Okay. Questions about that? Understand the trends, predicting those? Okay, you for sure definitely have a couple homework problems that are going along those same lines. Testing on that. Another thing we could do is look at the chemical properties for each of these elements. Okay, so when we look within a column, our physical properties tends to translate or have some relationship between them. Turns out our chemical properties are very, very similar. Okay, same general idea. Question becomes is, okay, what can we do with that? Well, if we take a look at lithium, let me back away from that. We want to look at common reactions. One of the most common reactions for anything to react with happens to be, it's up there, oxygen. Oxygen is one of the most common species involved in almost any mineral deposit because oxygen is relatively fairly reactive. So most things will form some kind of compound with oxygen. It's also relatively abundant in our atmosphere. And because of that and its reactivity, it tends to show up with a lot of your individual metals. Okay? So if we look within an individual column, let's say those are the alkali metals, we pick lithium. So if we know lithium, when it reacts with oxygen, holds the formula where we need 2 lithium atoms per oxygen. Okay, so that's true. Well, if we go to any metal underneath lithium, so this is one of the beauties of the periodic table, the chemical properties of anything in that column, it tracks the same. Which means if I now move to sodium, how many sodiums per oxygen would I expect? 2. And if you go through and take a look at all of the oxides for your alkali metals, you'll notice that we get the same formula for each of them. It's the metal, 2 of them per oxygen each time. Okay? It doesn't hold true just for oxygen. It holds true with any compound that we can take a look at. So for instance, this is a question that you could see on the test as well. Oh man, I forgot about this. Don't read that. The formula for the chloride of calcium is calcium or CaCl2. What is the formula for the chloride of barium? Okay, so there's a couple assumptions in here that you haven't learned yet. Why did we put calcium before the chlorine? Don't need to worry about that yet. We will be talking about that probably next week. Okay? By definition, we always put the metal before our nonmetal when we go through and put together a compound. Okay? So what we'll do to evaluate this question is figure out what's going on with barium. So the first thing we should figure out, what's the symbol for barium? Well, what is it? Ba. Okay. What is barium most like? Calcium or chlorine? Calcium. They're in the same column, which means we would expect calcium and barium to react the same with a chlorine atom or chlorine atoms. So what formula might we expect for barium chloride? BaCl2. Okay? Because we know barium and calcium are in the same family, they will react similarly. Okay, well that was an easy one because we could cheat and it was on there. So let's change it up. Let's say I want the formula for the fluoride. I don't like fluorine, never mind. The bromide of calcium. All right, so to do this, what do we need to do?
Well, do we have an example for another bromide in that column?
Nope. All the information has been given to you on this slide that you need to solve this. First approach I would do, what is bromide? Br. That's a bit odd. Why is it bromide and not bromine? We've changed the number of electrons around it, so it's the same element, but it has a different charge associated with it. Again, you don't need to know that yet. You will learn that shortly. Okay? Or tally if you prefer. Bromine, okay? Calcium, what's your symbol for calcium? Okay, what other information are we given?
The metal goes first.
Okay, so we could go ahead and do that. We're looking at calcium and bromine, X and Y. We don't know what symbols or what numbers should be going underneath there. Okay, until we understand something about the chemistry of those two. Do we have any information about the chemistry of either of those? Yeah, what information do we have?
Takes 2 chlorines to every calcium.
There are 2 chlorines for every calcium. Well, what's the relationship between calcium and calcium? They're the same, okay, so we won't predict much there. Chlorine versus bromine. They're in the same family, which means they would be expected to react the same. Which means the formula that we would come up with should be calcium Br2. Okay? Does that kind of make sense?
Kind of.
It takes a little bit, I'm not going to lie, because I'm pretty much removing anything to do with nomenclature, even how to put compounds together. There are rules that will help us predict how many of these things get put together. At this point, what we're trying to do is come up to these same formulas and arrangements that they were trying to do in the early 1800s, okay, or 1850s, trying to predict that chemistry. Okay, and so that was one of their cool things that they could do. They were actually able to predict that that chemistry worked out the same, which meant that when we organize the periodic table, chlorine and bromine should be in the same family or the same column because they reacted similarly. Okay, so that's part of the predictive powers of it. Why do we not put oxygen in the same family? Well, when we look at the formula with our oxygen versus our metals, do we get the same chemical formula? For oxygen, it took 2 metal atoms. For chlorine and bromine, it took 2 of the chlorine bromines and only 1 metal atom. So oxygen should not belong in the family with chlorine and bromine because it doesn't match that same formula pattern. Okay? Does that make a little bit more sense?
I found that on the test that had I had like a dozen practice questions that were, like specific to exactly how they were going to be presented on the test, I probably would have done much better in that written section, the first part of the test. So my question is, would it be possible, could I trouble you to come up with a dozen questions pertaining to this material that we could work through? Maybe extra.
What you're asking me, well, so that's what exactly it. You're asking me to write you a second exam. I definitely don't have time to do that. So what I did for that first exam was pull questions that are similar to your homework. Everything on that test had similar problems found in the text as far as the number of conversions.
I mean, there wasn't enough of the homework practice to be able to...
So what I would argue is you take a look at your textbook, the problems that I assigned, did you do every single question in the textbook?
Every single one.
Then you had all the practice that you could get, unfortunately. And it would come to how you were approaching solving those problems. So that's another big thing when it comes to homework. A lot of students come up to a problem and say, I don't know how to solve this. Okay? What should you do when you don't know how to solve it?
Google it.
Go to the textbook. One of the options is Googling it and trying to figure out some information about it. The problem with that, and it's the same thing that you would do if you went to the solutions manual, and a lot of students will go to the solutions manual, or go to a tutor and have the tutor tell them the answer. All chemistry problems, regardless of which subject, once you have the answer, are easy. Every single one. So the habit is that you go through, oh, I can't solve this, I need some help. You get some help from somebody, they help you, you figure out the answer. That problem is easy. What happens when I change the numbers or the words?
Right.
It's now an entirely new problem, and you have none of the skills
Right.
to be able to solve the problem. So when you approach a problem and you get help, it's not what's the answer. It's forcing whoever's trying to help you go through it very, very controlled stepwise. Okay? What are you doing? Why did you do that individual step? Okay? Why did you organize it where you started with the answer? Okay? Well, we started with the answer when we went through it in class so that we knew what our unit needed to be and where it needed to show up, be it in the numerator or the denominator. Then you go back to what other information you've got and find whatever unit that you're given and make sure that it shows up appropriately matching your answer. So if your answer is in time, what in the numerator, what unit needs to, or what type of unit needs to be in the numerator, and the problem, time, it has to match. Okay? So you have to be able to process through these. So I would argue that if you've done all the homework problems, you absolutely have all the tools you need to be able to do well on the test. At that point, it's probably test anxiety or simple mistakes, which is another unfortunate thing to do. Okay? So that's reevaluating all of your work. Regardless of what test takers say, don't go back and redo work. You can redo a problem, don't check your work. Checking your work is the problem. But you can retake the test. And if your answer comes out the same, then it's the same. So I can give you homework problems. Beyond that, I don't have anything else to give you because I don't have enough coursework built up to be able to do that, or time. Okay? There were another couple hands as far as this material goes. Forgotten? Okay. And yeah, it's unfortunate that I don't have that time, but I can't. I physically do not have the time. Okay. Chapter 4. So what we've gone through and done is started to look a little bit at the chemistry and the trends that they saw. Okay. And what they were doing with this is they really had no idea how this applied back to the atoms. They just said, oh, they had to come together in these whole number ratios. And we look at radii. Radii, that trend didn't make sense either. If we have more electrons, it should get bigger. Why on earth would it get smaller when we're going across the periodic table. Okay? And that comes from what's happening with those electrons. And to figure that out, we have to go back to the nature of light. Okay? So some people may have already heard of this. You get the particle-light duality, or particle-wave duality. And that's because electrons move in very odd fashions. They have both a particle aspect to them, which is our standard physical approach, and they also have a wave aspect to them. So what's going on with a wave? Well, if I talk at the wall, can you still hear me? Yeah, why? My voice is going to come out as a wave and spread all over the room effectively. Okay? What happens with light? If we turn on just a single light in here, we'll see light probably throughout the whole room. But if light was a particle, it comes out and boom, that's it. It only lights that one spot. It doesn't. Okay? Like throwing a baseball. Okay? When we throw that, it only hits the one spot. It doesn't hit all of the spots around it. So the question becomes is why? Well, that comes back to the nature of light being a wave, not so much a particle. Okay? So there's some aspects of the wave nature that we want to approach. There's a couple interesting things to address here. When we look at a wave, we can break it down into two main sections. Okay, what are those differences or those different pieces? Feel free to shout one out. We could look at wavelength. As this slide is trying to show, your wavelength is the measure going from peak to peak. Okay? So the distance between peaks gives you the length of the wave. Okay? Symbol for that is typically shown as lambda. Thankfully, we don't have to get too much in, or I don't think we'll get into any of the mathematics of this, so you don't have to worry so much about the symbols, but that's what that one is. Okay? So that's the measure between those two. What's the other thing that we could evaluate? Frequency. So what's happening in that case is we're taking a particular unit of time. That was a very horrible straight line. Let me try that again. Probably not going to be any better. That's a little better. We take a straight line and we say measure that time span. For each of these waves, how many oscillations did we get? Okay, well, in that top case, we went peak to peak. At best, we could say we went through one oscillation. What happened with the next one? Well, there's 1, 2, 3. We had 3 peaks show up within that, where in the other we only had 1. What we're measuring is the frequency. Okay? The number of our peaks within a standard unit. Okay? When it comes to frequency, it's the standard unit of time. Okay? So we get these two things that we can evaluate, both our wavelength and our frequency. I'll say right now that the relationship between those two, there is a mathematical equation for it. Slides don't have it on it, so that means I'm not going to make you responsible for it either. Okay, we'll focus on the two big ones, which I think are important, wavelength and energy. When we go through and try and determine the energy of these, the energy comes back to your frequency, okay, or shorter wavelengths. So, yeah. So low energy light has a very long wavelength. High energy light has a very short wavelength. Okay? So what you're going to be responsible for is knowing the relationship between your energy and your wavelength. Okay? And we'll come to another place where we can see that. If for some reason we had to do some math equations with it, and again, I don't think you do, the speed of light comes in at 3 times 10 to the 8th meters per second. You might have to do some conversions, but we're not going to do anything fancy beyond that. Okay? So those are kind of the components when we're looking at light. Next part about this is what things make up light. Okay? Well, when we think about light, we typically think about what part of light? Really almost always exclusively think about the visible range. Okay? Color. Light or visible light is just a small section of what's known as your electromagnetic spectrum, and that incorporates this huge range of possible wavelengths and frequencies. Okay, why is that important? Well, what we're looking at is just a tiny little band of information in here. Okay? So what we want to do is come up with some ways that we can incorporate our understanding of energy and wavelength back to these colors. So questions that I could ask would be, which color has highest energy? Well, with the picture, that might be easier to see. Okay, which color is the highest energy? Blue or red? Sorry, purple or red? Purple. How do you know that? Well, maybe you've already got it memorized, or you could cheat and see that the diagram says it decreases as you go towards the red. Okay, there's another way that I personally go through and remember that. Okay, what's higher energy than purple? It's on the chart. What's another name for purple? Violet. If we're going to have even a higher energy or a higher value for purple, we can jump to ultraviolet. It's so violet, it's ultra. Okay. If we go to the opposite end of the spectrum, what's a longer wavelength than red? Infrared. Okay, well, why does that help me understand the energy? Okay, well, let's think about this. Energy, typically bad or good, depending on how we control it. If we go outside, okay, what's one of the things that we're typically told to take care of when we step outside? The sun. We put on sunscreen. What's the point of putting on all that sunscreen? You're trying to protect yourself from what? What causes the skin cancer? UVA, UVB, UV for ultraviolet. Okay? We don't walk outside and put on our sunscreen to protect us from infrared. Okay, why? Because ultraviolet is higher in energy. We're scared of the higher energy things. Okay, so we're trying to put on a protective coating away from that higher energy system. Okay? So all I need to remember is the difference between ultraviolet and infrared, and just think about going out into the sun. And now I know ultraviolet is higher energy. Whichever color is closest to ultraviolet should be the higher energy. Okay? Which color is closest to ultraviolet? Purple, or our violet. Okay? And our red then would be the lowest energy. Okay, so then that brings up the next question. On a test, can you imagine me printing out a nice, beautiful color spectrum like this?
Yes.
Unfortunately, no.
You could put it on the screen.
I could put it on the screen. I'll consider that. But there's another way we can get around that. Okay, there's a famous person in our class by the name of Roy G. Biv, standing for red, orange, yellow, green, blue, indigo, and violet. That puts together the color spectrum that we would expect. Granted, it's now inversed from what's supposed to be on there, but again, you could come back to it and say, okay, which was higher energy? Ultraviolet, which means which color is going to be our highest energy? Our violet or purple color, and we've got high energy. Which then also means what's low energy? So yet another thing that we could write on our test. And the wait a minute is probably coming from how it's referenced. Low energy versus high energy, you'll notice, is inverse from what the diagram shows. Why? Because the diagram is showing not Roy G. Biv, but Vib G. Yor. Right? I think I did that right. It's inverse those colors on you.
So the higher the frequency, the lower the energy.
I don't even want to bring in frequency into it because I honestly get that confused and have to go to equations. That's why I'm not going to test you on frequencies. But energy, I will test you on.
Okay, so the more peaks, the lower the energy, the less peaks, the higher the energy. Reverse that.
I think you got that reversed, yeah. And you got two people telling you it's the opposite, so there you go.
I'm confused. How would you make this into a question that we would answer?
Which of the following colors is highest energy?
Okay.
Orange, yellow, green,
I would get that.
indigo.
Okay.
Yeah.
Talk about weird stuff over here.
Okay. The other thing we could bring in is the wavelength. Wavelength is going to become important as you deal with more things in the color spectrum, so I do expect wavelength to show up. That's one that you would just have to have memorized. Your violet shows up at what wavelength? Your 400 nanometers. Your red shows up, according to this, at 700 nanometers. Okay. You would need to remember that. So which of the following colors has the highest wavelength? Orange or green?
Green.
Higher wavelength means
Not energy.
bigger number. Which number is going to be bigger? Orange or green? Which one's closer to the bigger number?
Green. No.
Orange or green? 700 is here.
What's that? What's the end?
400 is there.
Nanometer.
Which one is closer to our bigger number? Orange.
And that's
Okay.
in regards to its length.
That's in reference to the wavelength.
Wavelength.
Yes.
Okay, so the higher the number, the lower the energy. The lower
For
the number,
wavelength,
the higher the energy.
yes. Okay. Questions about that? Okay, it is difficult to keep that together. Like I said, when I go through and do it, I always deal with the formula. Since they aren't throwing the formula at you, we'll try and avoid dealing with formulas. Yes?
I'm sorry. So how does the number of nanometers, I guess it's nanometers, right?
Mhm.
How does the number of nanometers relate to the
Don't say frequency.
wavelength?
The number of nanometers is the wavelength.
Is the wavelength.
It's the distance between it.
So
Nano and what's the M? Meters, which is a measure of length, wavelength.
between the peaks. Okay, so the lower.
Okay. Takes a little bit of getting used to. That's why I would write out the Roy G. Biv thing and put the numbers down to it. There's no ability to swap at that point. When you try and go through and keep this in your head, guaranteed you'll confuse it, because I'll confuse it too. So what should you do? Your name is pretty important, but I'm pretty sure by the end of the test, you'll still remember your name, right? You should say yes to that.
Yes.
Okay, yes, you'll remember your name. So what you can write down instead, Roy G. Biv, high energy, low energy, and your wavelength numbers. You no longer have to think about it. It is already patterned out for you. Okay? So why are we looking at this? Well, this comes back to how this information was used to figure out where our electrons existed. So a man named Bohr came along and took a look at light, and in particular how light passed through different elements and how it responded around different elements. Okay? So what was predicted is that when we look at an individual color, okay, or a spectrum, we would expect to see this continuous spectrum. So if we excite an individual sample and we just have a sea of electrons, what we would hope or expect to see is a continuous light spectrum coming out of it. Okay? We don't see any bands. What do I mean by bands? I mean this. If we take a sample, mostly empty tube, and we fill it with a particular element, in this case hydrogen, okay? What we're going to do is pump a whole bunch of electric energy into that. Well, that electric energy has to go somewhere, and it ends up going into the molecule, or sorry, into the atom. And it does some crazy stuff to the atom. That atom then needs to relax back to its ground state, get back to a stable state, release that energy. In the process of releasing it, it's going to give off that energy as light. Okay? If it was a sea of electrons with no real shape associated with them, what happens? We would expect to see all sorts of different electrons at all sorts of different energy levels, which means we see an entire spectrum of possible colors coming out of that when we split it through a prism, much the same way that we see white light. What Bohr actually saw was not that. In the case of hydrogen, instead of seeing the full rainbow spectrum, he only saw 3 lines, 3 colored lines. Okay, and he took this to mean something very important. What he said was that what happened within the atom is that instead of seeing a continuous random mass of different energies, there's very distinct energies. Those very distinct energies must be where our electrons are existing, or where some subatomic particle is existing. Okay? At this point in time, they'd already defined what was going on with your nucleus, so they really had no other option but to assume these colors were coming from electrons. Okay, so what does this mean? Well, what the result is that we get a discrete energy level as opposed to continuous. Okay, so Bohr went through and said instead of a sea of elements or a sea of electrons around a nucleus, I know this image is not the greatest. So we've got our nucleus in the center. What we had on the outside, I don't know if you guys did this in high school or junior high, but I know when I was back then, they had us glue a bunch of pennies and stuff to circle rods, made little mobiles, and spun, oh, we made an atom. Okay, it's not exactly that neat. Okay? But what he's saying is that the electrons exist in very particular patterns. So that when we start with an atom in its stable state or its happy state, we're going to put that first electron in as low energy as possible, so as close to the nucleus as possible. Why should the electron want to be as close to the nucleus as possible? Okay? Interesting observation with chemistry. Everything strives for neutrality and low energy. If we have an electron floating off on its own, what's its charge? Negative. What happens when you bring that negative charge near something positive? Starts to neutralize. So when we look at our orbitals or our atomic structures, we're going to try and get our electrons as close to the nucleus as possible. Try and stabilize that charge. Okay? So that's hydrogen in its standard state. Then Bohr comes along and says, you know, that's not very exciting. So electron, I'm going to zap you with a bunch of electric energy. Whoa. Jumps up to a higher energy state. Pushes that electron further away from the nucleus. Okay? So imagine you walking along and all of a sudden getting pulled way up into the sky. Okay? Particularly nice thing for you. You're just going to be, oh, wee. You're probably going to. You're just walking to class. Just walking down the street, la, 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 whoop, you're 100 feet in the air. Okay? You're probably, if you don't pass out and pee your pants and freak out, okay? Electron's going to do the same thing and say, this is ridiculous. I want to get back to my happy neutral state. So it may hover around that high energy state for a little bit, but eventually it says, you know what? I need to go back. So it'll jump back down. But here's the problem with that jump back down. To get up to that higher energy state, it had to absorb electric energy. We had to give it that with our electrical lamp. To go back down, where does that energy go? Remember, our first law of, or it's not a first law yet, what was our rule? Law of conservation of mass and energy. Okay. We cannot create or destroy matter or energy. If we relax that back down, that energy must go somewhere. Just so happens to randomly be that that energy matches visible light. So what ends up happening as our electron returns back to its ground state, it emits light. Well, what's the energy of that light going to be? It's going to be equal to the energy difference between the excited orbital and the ground state. It can't be anything in between because the electron didn't exist at any of those other in-between states. It was only at the excited state or the ground state. Which means when we look at the emission, we see a single line. Okay? We see a discrete energy of light, or a discrete packet of light energy due to that jump. Okay? So this is kind of a huge advance as far as our atomic structure goes. We now have a way to represent our electrons being around the nucleus in very distinct orbitals, okay, or distinct homes. Okay, massively, massively important.
This test only works if the element's in its gas form?
Yeah. Not that important to know, but yes. What this is referring to, or is derived from, is the quantum concept of the atom, okay, and particularly electron orbitals. Put very, very simply, what we're looking at is discrete versus continuous. I keep saying those two words. If it was a continuous system, what we're saying is that we take our sea of electrons, and our electrons can exist anywhere on this curve. Which means when we go through and excite them up to a higher energy level, they can go back to any point along that. Which means we see a full spectrum of light. Okay? When we go through and look at a discrete energy system, our electron starts at the ground level and always wants to be at that lowest energy state. There is no intermediary position. We can then excite that electron, but we can only excite it up to a step. Once it's at that step, it can now fall back down, but only to another step. Each of those step differences represents a level of energy. Does it make sense for a step to represent energy? When you climb up the stairs to the building, do you get a little bit tired as you get to the top? Why? Putting in energy. Okay? You have to give up the energy to move up. Okay? Same kind of thing. If you fell back down, you'd end up releasing that energy in some form or another. Okay? So that's what Bohr's theory is really coming back to, the discrete energy levels. Okay? Questions about that? Okay. So, again, back to our picture. If we take a look back at Bohr's system with our energy diagrams, he ended up again doing, these are really bad circles, but you can't see what I'm drawing over, so it's okay. Bohr's system went back into some hardcore mathematics to explain what was going on with each of these individual colors that were detected. And it turned out for the hydrogen atom, what we were looking at is an electron being excited. Okay, it's going to start in the ground state. We'll excite it up to the third, fourth, or fifth energy level. Okay, just like with the stairs, our electrons can now potentially relax downwards. Do they have to jump back to the first energy level? No, they could jump just to the second, okay, or to the third, to the fourth, depending on which level they are, as long as they're always going downwards. And it just so happened that our energy to go from the third to the second, that release of light happened to match what color? Red. What happens when we look at, what's the next one? Green? When we look at our electron going from the fourth to the second. Okay, it starts to become this green energy. Okay, well, what's the energy gap? When we look at from 3 to 2, how big of a distance is that? What is that? Depending on where I hold the pen. Okay, the thumb, it's an inch. Okay, king's inch. What's that distance represent? Energy. It represents the energy. As we get further away from the nucleus, what happens? The energy increases. So when we jump up to the fourth level and we jump now back down to the 2, we're looking at what? 3 thumbs. The energy level for that transition goes up. So what should happen to the light? The color of the light, if the energy goes up, it should start to shift more towards purple. What happens for that last one? When we jump from 5 all the way down, 5 down to 2 gives us the purple light shown in the spectrum. So the larger that jump, the higher energy of light that is emitted from them. Right? The smaller the jump, the lower energy light. Yes?
I'm just trying to see if my question even makes sense. Because wouldn't the red one, wouldn't the wavelength be shorter, but I don't think that light, so it doesn't really matter.
So the distance is not a distance measurement, but an energy measurement first off.
Okay.
So before we get into a picture that I personally like a little bit better, turns out each element can do a similar process. Okay, so what we can go through and do is put it into the gas phase, because it needs to be in the gas phase to pump this electric current through it. Okay? Once it's in that gas phase and we pump in our electric current, it will emit particular light. Okay? Different colored light. Does it make sense for it to emit different colored light? Please say that's right. Well, when we look at neon, argon, all of those, what happens to the color of our neon lights? We get different colors. The only reason we get different colors is there's different gases in each of those tubes. Those different gases are what are contributing to those colors. Okay? So each compound has its own emission spectrum. Why should it be different? Okay? A hydrogen with one electron, that first electron is going to go in the lowest energy system, or the lowest orbital, right? Well, when we go to helium, where's that next electron going to go? Still, its first electron is going into the lowest energy orbital. Why would its spectrum change? There's more electrons. There's also more protons. All of that is changing the energy of the electron in that lowest orbital. Maybe not a lot, but enough that we see a different spectrum. Right? So every compound is going to have its own atomic fingerprint. It's in reference to the actual orbitals that actually make it up. Okay? And each of those is going to have a slightly different spectrum because each of those orbitals is different from another element. Because there's more or less electrons, more or less protons, changing the energy of the overall atom. Okay, so it's kind of neat. Questions about that? Okay, so then we get our different lights with our different noble gases. So now let's kind of get back to what's happening with this. So Bohr, the whole point of all of that material is really to come to one conclusion. That electrons exist in orbitals. They have a home in which they belong. It's not a sea of electrons completely floating around the atom. They are in very distinct places. Okay? Bohr went through and evaluated different energy levels. So we can look at 2 energy levels to start. Okay? And we're going to put energy on our y-axis. So if we were going to draw on an axis here, we could say energy going upwards. Okay? What do you think the blue line represents or the black line? Take your pick. I personally think the black line's a little bit easier. Nope. The black line represents the orbital closest to the nucleus, the lowest energy orbital. So if I'm going to put electrons into my structure, that's where I'm going to put them first. What's the blue line represent? The absolute highest energy state for an electron. What's the absolute highest energy state for an electron? Right idea, farthest away, so far away that it is a free electron. It's not attached to an atom. Because at that point, it's so high in energy because there's nothing to neutralize that negative charge. Okay? So what we're looking at is the complete lowest energy state, where it gets as close to the nucleus as it can without spiraling into it and destructing. The maximum is as far away from the nucleus as possible, such that it's not even bound to the nucleus. So it's no longer part of the atom.
Can we do that?
Yeah. You can completely rip an electron away. Theoretically, yes. Yeah. Okay. So now what can we do? Well, we'd want to fill in our other energy levels. Okay? These colors are not there for any particular reason. I just wanted to show them as different colors, so they stood out a little bit differently. Don't match these back to the different energies. Okay? So we now have more orbitals, okay? More homes for our electrons. So they're going to increase in energy, and they're going to get further away from the nucleus as we add more electrons in. Why does that make sense? If we move from lithium to sodium, okay, lithium has 3 electrons. Why, when I put in, what's the math, 8 more electrons, would those electrons be further away from the nucleus? What's that?
There's no room, right?
Kind of. Why would there not be any room? What's the charge on an electron? What's the charge on another electron? What happens when they get near each other? They repel away. So I can only put in so many electrons into each energy level before I now have to shift to a new energy level. Okay? Because the electrons start to repel each other and they get pushed into a different orbital. Okay? Or to a different level. Okay, so that's not too bad, at least at this point. We've got a whole bunch of different energy levels. We just kind of put our electrons into it. Of course, it can't be that simple, right? So what ends up happening? Well, those energy levels can split. They split into different types of orbitals. Okay? You'll notice that for our lowest energy level, how many types did we get? Lowest energy level was what color? Black. How many different orbitals did we get? Just the one. Okay? When we move up to energy level 2, how many orbitals do we get? Now we get 2. When we move up to 3, 3 possibles. What do you think for 4? 5? 5 possible types. All right? So, geez, man, that's starting to break down and become even more unbearable. There's no way that could possibly get more complex, right? Sorry. We can now potentially look at the orbital orientation. And thankfully or not, I didn't actually split it up. So we've got our energy level, we've got our orbital type, but then each of those orbitals, when we adjust how they look in space, classify as a new orbital. Okay? Can't get any more complex than that, right? Also bring in something known as the electron spin. Okay? So we can generate now a whole bunch of different energy levels. Each of those energy levels has different orbital types. Each of those orbital types can split into different orbital orientations. So we end up with orbitals upon orbitals upon orbitals. Each of those single orbitals can now hold 2 electrons. But wait, what happens when we brought 2 negatives near each other? They're repelled. What's going on with electron spin? Why can I put more than 1 electron in an orbital?
If they have different spins, you can actually put 2 together.
Yep. So what's happening there? This goes all the way back to your quantum mechanics. An electron, pretend it's a sphere, okay, a little ball. It spins. If it spins clockwise, cool, it's spinning clockwise. What happens if it gets near one that's spinning counterclockwise? Well, it turns out that negative repulsion's minimized. And they go, oh, okay, you're not completely like me, I can accept that, and we can live together. Okay? If they have the same spin, though, what happens? Now they repel away from each other and they have to jump into different energy levels. Okay? So it's kind of a complex task as far as all these are broken down. Where these ultimately come from is something known as Schrodinger's wave equation. I really tried my best to get an equation that showed all of these on it and didn't do a very good job of finding that. Very complex mathematics on it. Feel free to look it up on Wikipedia. It's not a particularly pleasant read through, but maybe you'll see how interesting it can be. It's absolutely amazing to watch someone derive this. Okay? So unstable elements are changing not because of electrons, but because of their nucleus. It's a separate issue. Yeah. Where do the electrons live? So after all of this, we want to bring back some understanding of this. Everybody goes, oh my God, this is way too difficult to deal with. Okay? So ultimately all this is dealing with is where the electrons live. Okay? So where do you live? Okay? You got a house. How do you get to your house? What do you need? You need an address. That address or that number on what? On a street. Where's that street? It's in a city. Where's that city? It's in a state or a county. I didn't even think of county. Okay? So ultimately what we're looking at here is an address for where electrons exist around an individual element or around that nucleus. So what we're specifying with each of these pieces of information is part of that address. Your state, okay, that's the largest aspect of that. That's your energy level. The city is looking at the type. Okay, what orbital is that electron in? What kind of type is it? Your orbital orientation is what street you're in within that city. And then the last part would be your address, okay, the street number where the electrons spin. Okay, we'll go ahead and end there and pick up again on whatever it is, the next one.